And it might do that. And why not? It's just for you guys, not for anybody else. But so alkenes, we've got a little summary of what you need to know for alkenes for IB chemistry. I might not get through everything, right? That's not my intention. It's to revise and review with you the sort of things, the basics that everybody should know and we should all be getting right every time. So we kind of get the base scores up a little bit, I would say. And I might not have already told you this, but you will be doing another organic test. I've got lined up another organic test for you, which I've written. It's hard, but it's needed, right? Because you didn't do as well as I'd like you to on organic. So let's review alkenes and make sure we know what we're supposed to know for alkenes. So I just want you first of all to know all of the reactions of alkenes. So very basically, you should be able to recite this. This is a kind of memory thing. If you don't want to copy this out, you don't need to. You should absolutely be able to reproduce something like this from memory, which are all the reactions of the alkenes, which I'll just sketch out for you now to show that you can add a halogen across the double bond. You can add HX, so HCl, HBr, HI across the double bond. And you can add water, but it must be as steam across the double bond in the presence of an acid catalyst. And this is probably the one that people find the hardest to remember. So make sure it's on your revision sheet and you've learned and practiced that you get alcohols from alkenes with steam in the presence of sulfuric acid. Or you can add H2 across that double bond in the presence of a catalyst, nickel. Bit of pressure, bit of heat to get an alkane, a reduction reaction. And we're going to do a session like this on oxidation and reduction as well. And the thing that all of these have in common is that they're all electrophilic addition. Okay, they're all addition reactions, and you need to know them, that they're the mechanism really of this reaction. It's electrophilic addition. So you quite often get asked in exam papers, what type of reaction is this? Electrophilic addition. So I want us to think a little bit about bonding and why alkenes react as they do. It's an opportunity to practice bonding as well, and what we mean by electrophile as well. But just as a little aside, I just remind you that you can also burn alkenes, and you can combust them in oxygen to give CO2 and H2O. But they're quite likely also to undergo incomplete combustion, giving you carbon monoxide and carbon soot as well, which we know for sure. Right, so electrophilic addition comes about because of the bonding of alkenes. Now with the other group I got them to draw what they think a pi bond or a double bond looks like, and it was pretty ropey, frankly. So I'm just going to draw it for you to save a little bit of time rather than embarrass you all. So I'm going to draw this alkene showing the sigma bonds. So about half of you have learnt it, I'm guessing, and about half of you haven't. So that's the kind of sigma bond network that alkene would have, right? So it looks something like that. These are all sigma bonds. And if you're drawing diagrams like this, please label the bonds. So I'm focusing particularly on the carbon-carbon double bond. And so I'm only going to label the sigma and pi bond for that. Now this comes about, doesn't it, because the carbon is sp2 hybridized, and so these three molecular orbitals come about from the overlap of the sp2 molecular orbital made by carbon. So 120 degrees from each other, pointing like that. One bonds with hydrogen, one bonds with hydrogen, and the other bonds with the carbon. That comes about through end-on overlap of the orbitals, the sp2 hybridized orbitals. Okay, so there's an overlapping, and that's a strong bond. It's stronger than a pi bond, and it's stronger because the electron density is between the two nuclei. If you think about it, all a covalent bond is, and I've got some notes from the last lesson, but all a covalent bond is a pair of electrons between two nuclei, gluing those two atoms together, if you like. The pi bond is the region of electron density which comes about from the overlap of the other atomic orbital, the p orbital, so there's this sideways overlap between the two p orbitals, and this whole thing is where those two electrons reside, either above or below or both, right? But this pi bond is weaker than the sigma bond because the electrons are further away from those nuclei, which is why a pi bond isn't quite as strong as a sigma bond, and it's why that pi bond is available to undergo chemical reactions, which is why alkenes are more reactive than alkanes, which is why they act as nucleophiles and react with electrophiles, hence electrophilic addition. Now you're expected to know for the IB that electrophilic addition, or what an electrophile and nucleophile is. An electrophile, yes, it's something that likes negative charges, which is kind of how we've described it. But we also need to think of it as something that, so electrophile is something that can accept a pair of electrons, right? So that's the definition you need to go on your flashcards. So accepts pair of electrons. That's what an electrophile is. And addition is the whole two becomes one thing. Two molecules become one molecule. And so that helps us think about the mechanism and learn that mechanism a bit more easily, hopefully. So electrophiles accept pair of electrons. This is a nucleophile because it's donating a pair of electrons or giving away a pair of electrons when it does the reaction. So let's remind ourselves of the mechanism then. So I'll write it out again. And I've got it on this sheet already, so I'll just go through it with you. We've done this so many times, you've practiced it so many times, but look, the key thing is that you're showing the movement. You don't need to copy it out now because you've got this in your notes perfectly already, right? So don't copy it out, let's just talk about it. If you like, a way of thinking about a double bond is that one of them is a sigma bond, if you like, one of them is the pi bond. And the pi bond is what's giving away or pushing electrons towards the delta plus hydrogen of the HCl or HBr or whatever. Okay, so getting that arrow starting from the right place makes sense, doesn't it, if we think about it coming from that pi bond, which is why alkenes are reactive. And it hits that hydrogen because the hydrogen is slightly positively charged, because hydrogen is not as electronegative as the halogen X, so it's a polar bond. Hydrogen can only make one bond, and so this bond forming process here causes this bond to break, and that leaves us with the carbocation, and that's where we start to sort of slip up. We don't draw the carbocation necessarily perfectly, and then we attack that carbocation with the lone pair of the halide that's formed, and people forget to draw the halide sometimes, and you end up with the product, right? That's all fine and generally pretty good. But where it gets a bit harder is with unsymmetrical alkenes. When I say unsymmetrical alkenes, I mean alkenes that haven't got HH on both sides. So on one side is HH and the other side is not HH, it's H and then maybe CH3 or an alkyl chain. And so you then have two possibilities. It's going to be an addition reaction. This H could either go on this carbon or this carbon, and likewise for the X. And you need to know which way around it goes primarily and why, and the language that goes with that. And in your test that you did a couple of weeks ago, it wasn't the mechanism that was so bad, actually it was the explanation of what's gone on and why that needs polishing, and that's what I want to practice with you in the last couple of minutes we've got together today. So that bit's the same, right? The pi bond attacks the delta plus hydrogen. The single bond here breaks to form the halide again, exactly as before, and you end up with the carbocation as drawn there. And again, you've already got this in your notes, you don't need to draw it again. But what we have to do is to recognise that the carbocation could have formed on that carbon or on that carbon, and you need to draw it on the right one, and you need to say why it goes on that one. And I think, talking to the group last lesson, it wasn't perfect because people didn't really understand it. So you have to count the number of carbon chains, or alkyl groups, around that carbon versus that carbon. Now this carbon's got two alkyl chains. It's got one carbon chain, and it's a very short carbon chain, another carbon chain. It's two alkyl groups, two carbon chains around the carbon. And that means that carbon, that delta plus carbon, is more stable. We talked about the reasons why in a previous lesson. I'm not going to go into that. What you need to say in your exam is what's written here. So if you could write down this as something that I'm going to test you on next time I see you, you've got to say the more stable carbocation forms preferentially because it's surrounded by more electron releasing alkyl groups. We can talk about the positive inductive effect, and that leads to the major product. It's that language which goes on the flashcard that you're going to practice for next time. And I've drawn the major product quite scruffily underneath. No, I haven't. I've drawn a mess underneath. You can ignore that. You know what the major product is. So positive inductive effect. That's this idea that electron density is pushed towards the cation from the alkyl groups. How that happens we don't need to understand, but we have talked about in the past. We're not going to talk about now. Just know that alkyl groups push electron density towards it, making it stable. More stable carbocation formed preferentially, surrounded by more electron releasing alkyl groups. Positive inductive effect, major product. Causes the major product. Get those ideas across in sort of whole sentences in your answer, and you'll be in a good place. That will be in the test that I give you. It will be asked next time. Was it next time I've got the test? When's the spectroscopy test next lesson? What have I got you before then? Got you tomorrow. So I'm going to ask you this tomorrow, folks. Yeah, and we'll do some more on these lines tomorrow. We'll stop there. Please continue to learn spectroscopy and practice it, and I'll see you then.